Okay, so we probably have everyone back in. It's still a minute before we start, I guess, but let me just have a look outside. If there's everyone, we can start and then have a quicker lunch, right? Będziemy zaczynać. A few more people coming in. All right, so the next person I don't have to introduce too much because it's myself, so I'm just going to talk a few more words later on. I'm not sure how many of you have had this situation happening that, you know, you look at some new system, some new code, and then you see, okay, this is what they wanted to do, but why did they use this basic algorithm for this? You know, why is it like n squared, not n log n, or whatever, you know? I mean, for me, it matters quite a lot. I just think it's cool, and this is the sort of magic part here, that algos can give you, you know, thousands times speed up on your problem, for instance. And such a case, I actually want to walk through with you today. This is a case coming up from one of the business cases that we looked at. I think it's pretty interesting. I did some experiments on this, so I hope you will find that interesting. I work at Virtus Lab as a head of data science, and supposedly we do all those things. I won't go through all of this, but you know, the slides will be available later if you're interested. So, as I mentioned, we'll start with the business case, then we'll go to the actual problem being just part of solving that business case. We'll go through a few solutions, then I'll walk you through some of the experiments that I've made, and maybe just show you code which is going to be using quite a nice package, GeoSpark, for spatial data structures and processing. Right, and this thing, you know, the big data and small data, you know, some of that is relative. Like if you use good algos, then maybe, you know, you can process something 1,000 times quicker. So instead of running that on a cluster, you can run it on one box, right, if you use one algo. Right, so the case I'm talking about is the retail challenge. What you have here is you have your happy customer at the end. And for those of you who actually have been here, were here last year, you know, this is a similar slide that I was showing because it's similar area or domain that we are looking into. But don't worry, this is not the same presentation. But just for the beginning, you know, there is this happy customer at the end who receives some products. Those products need to be produced somewhere. There is some logistics involved for that product to go through the warehouse, go through the store, or maybe ordered online. Then there is a van delivering that product to the customer, maybe. And the case we're talking about here is just a subset of the whole thing, which essentially is looking at those vans. So how do we optimize the delivery? Well, an example question could be, how many vans do we need to keep, right? Do we keep 10 vans, 1 van? What is enough, right? Can we optimize it so that we do not require to have 10 vans, but just can do the same job with 5, right? So this is our case. Now, here you might recognize, do you recognize what this place on the map is, maybe? Someone from Krakow, yeah, obviously here is Wawel. Oh, actually Wawel, you can't see it, but it's right here. Anyhow, so you have those 2 routes of 2 vans, 2 deliveries. You know, one was delivered here, the other one was delivered there. You know, could we do that using just 1 van? What we need to answer that question is quite a few things, but one of those would be, you know, how quickly can you deliver the thing from A to B, right? So if you are able to say, so just coming back, if you're able to say, how long does it take me to get the, you know, the stuff, the product from here to here, and here to here, and, you know, then you can see how much products you can actually deliver with 1 van, or do you have to have 2 vans to deliver it, right? So that's a pretty basic thing. So the way you could approach this, you could predict this delivery duration So let's imagine we have this route here. What you could use your data of your historical trips, right? So if you fitted your vans with GPS devices that actually create the stream of GPS points along your routes, then you could use those points to calculate the average speeds on the roads, right? So for instance, you would know if there is, obviously if you have quite a lot of deliveries, you have hundreds of vans going through the same road, over time you can say, well, the average delivery time on that road, sorry, not delivery time, but just the average speed on that road is this and that, right? So you could do that. And this is this very small and maybe tiny bit of the whole optimizing problem, but let's just focus on this one tiny bit. So what you have your historical GPS point stream, and this is the stream, the blue triangles show you the stream. So essentially as it goes, some of them are off the road just to show that they might not be perfect. There is some precision of those points, and some of those that are outside of that road, obviously, are quite outside, just to demonstrate that. You also had the circles here. If there is a green circle, that means it actually catches a road, right? So these catch the road, so these are probably pretty good. So there is some diameter, let's say 10 meters. And those that are red, they do not catch any road. That means they are, probably not good points to use, right? Because the GPS got so far away that maybe we just don't want to use it. Right, so again, as I mentioned, the algorithms I'm gonna talk about, if you look at a system, you're gonna be, it's gonna be pretty likely that you're gonna see a basic algorithm. And when you actually start thinking about it and saying, okay, we can do it this way or that way, there is about 1,000 times speed up that you can get by just using some more, involved algorithm. And by the way, I'm not suggesting that you should always do that. And when I look at these systems and say, oh, why haven't you used n log n instead of n squared? Obviously, I know why, right? This is business. You have timelines, time frames, roadmap, and maybe this thing that you want to speed up is such a little portion of your whole system that overall, even if it gives you 1,000 times speed up in this particular problem, for the whole business problem that you have, it's just going to give you 2% increase, and your code is going to be more complex, and so on and so forth. So in business, this is why it happens. Obviously, we're at the conference now, so we don't have those restrictions, and we can have a look deeper inside. So how to map those GPS points to roads? So I'm going to go through these three things that came to my mind. Obviously, there can be more, right? This is not everything that is possible, but the most simple thing that you might have, how many of you actually used Apache Spark as a tool? It's pretty standard in big data world. Okay, so some of you. So just as a small introduction, Apache Spark is this platform for an API for data processing, for big data processing, especially for distributing that processing across machines, possibly on Hadoop cluster. Right? This is how it's used in a big way currently. So a simple solution to our problem of mapping GPS points to roads would be, okay, so let's just take Apache Spark. You have the data set, which is stream of points, and you have another data set, which is a map of the roads, right? So there is a road map and stream of points. And what you can do in Spark, for every point, you can just join it, try each and every road, and check whether that point fits on that road or not. And if you find, or within some distance of the road. And you would use some geometrical stuff to try and do it. So this gives you n times k, because there is n GPS points and k roads in our data set, so this is the complexity, right? Solution number B, you can go a bit more clever and say, for every point, I can, well, actually, for the roads, I can store the roads in some special data structure that allows you to look up a road in logarithmic time. So there is special spatial data structures that allow you to do that. And there is this, well, add-on to Spark, which is GeoSpark, that allows you to use pretty easily such structures. All you do, and we'll see that in the code later, all you do, you have your one data set and second data set, and you just join them together. That's all you do. And underneath, it actually uses the indexing on the special spatial data structures that will make this complexity n points times log k of the number of roads. But, you know, just going further, you might not use any of the big data tools and just go for, you know, plain old program, and you can actually get, you know, just remove this k completely. Any ideas how you could do that? Anyone? Okay, pretty basic thing of just caching what you have. So if you imagine you had this map of points to roads, and before you start your lookup, you just generate that map. So you might even go with this algorithm and spend a long time to generate your mapping, right? Then you could, if you had such a map, then your lookup would be constant, right, for a given point. It doesn't depend on the number of roads, right? Because you can have just a hash table and look up that point. The only problem is, you're not going to do it, you're not going to cache each and every possible point that you have on the map, right? So that's the little thing that you have, and that's why you have this discretize here. Because sometimes it might be possible to actually use this sort of approximate solution where you don't do it for every point, but maybe if you have, you know, once every 10 centimeters, just for the points, you know, that are far away for 1 centimeter, so you build sort of a mesh over all your space once every 10 centimeters, then you might say, you know, GPS is not precise enough anyhow, so I can just as well just do it for those points in my mesh, and then for any other points, I can just bring it to the closest point and look it up in the table, right? It doesn't have to be 10 centimeters, it can be 10 meters or 1 meter, whatever it is that the GPS precision is, and it's good enough for you. So if you're able to sacrifice this, and as I say, sometimes it's very reasonable, you actually get to, you know, ON, which is pretty cool, at least, you know, for me. So just as you know, a little theoretical thing, so you have a simple thing, if you had 1 road, 2 roads, and so on, or 1,128, and then we assume that endpoints have some unit cost, right? Then the algorithms would compare like this. So ON would always have the unit cost because it does not depend on the number of roads, as we mentioned. ON log k would have, you know, just grow pretty slowly, and NK, the simple one, would grow, you know, the same way as k does. And this on the logarithmic scale looks like this, right? So this, I use logarithmic scale because otherwise these two guys here at the bottom would have been on sort of the same spot. You wouldn't see the difference, but there is actually huge difference also between, you know, the second and third thing here. So maybe let's just dive a little bit into those solutions. So this naive solution, we talked about it a little bit. So you have endpoints for every point. You go through all of the k roads, check whether that point is on the road or not, and that's it. Obviously, what you might say here is, well, okay, but if we put our data set in regions and put our points, so our roads in regions and our points in regions, then you only, for a given point, you only need to check the roads in the region rather than check it somewhere outside, right? So you might speed that up. And of course, you can do that. So it would more or less look like this. Again, that is Krakow, and you have it divided into some sample regions here. And if all of those regions, so this region would contain all of the roads that are within that region, and so on for the other ones. And then you would have this partition here, you know, this little disk that is to represent the partition, those roads are stored on this partition, those roads are stored on this partition, and so on and so forth. And now if you take the stream of points here, let's say there is some trip, van trip, and you organized it so that this van trip is also stored only on this point, on this partition, then you could only just match those points to the roads on this partition without checking anything else, right? So you could speed it up in that way. Obviously, you have to be a bit clever how you do it, because these trips can span quite a few of the roads. Moving on to the second solution, when you use GeoSpark, this co-partitioning is actually built in. This is part of creating a data set in GeoSpark. You just say what sort of indexing or spatial data structure you use underneath, and that's it. It's gonna do this thing for you for free, right? So this is pretty cool in terms of GeoSpark. And obviously, it also adds, once it has this data structure that co-partitions it, it also creates this indexing for you. So you have this log k very easily, as I say. And again, we'll get to the code soon. From the GeoSpark paper, I actually contacted the guys here to ask whether it's okay to show some of the shots from their paper, and they agreed, obviously. So they had this nice summary of what the spatial data structure, how they help you or how they work. So you can divide your thing, your map, in uniform grids. Obviously, it has a problem if you have a grid here which is sort of empty, there is nothing there. And you have one that contains quite a lot of points. You have this imbalance in your partitions, which is not great. So the other ones might actually address it in some way. So you have a quad tree, for instance, where you essentially are able to divide those things further down till maybe the point that you realize that, okay, yeah, probably the balance for the data points is right. Similar thing happens with R trees. Again, it's a different approach. We're not going to go into details here, but just for reference. And there is KDB trees that work also to mitigate that problem. Okay, and our final approach, as I mentioned, you can have this lookup table and create it. As we mentioned, this is an approximate solution because you don't cache each and every imaginable point. You only cache a mesh of points. Just to illustrate this, if you only cache these points here, so this, so there is this mesh of points. So if we cache this point and we say, okay, for this point, there is no roads around it within 10 meters, and we cache this answer, right? And for this point here, oh, there is a road, because that's the road here. So there is a road, so you have it cached. So now if we have a point that you try to look up, and this is represented by this blue triangle, then we might say, okay, well, actually this triangle should match at this point here, but maybe for simplicity, you just sort of bring it all to this point. This is what I used for the simple experiment that I had. But it's, you could approach it both ways. But anyhow, when you want to look up such a point, very simple arithmetic operation can just bring it back to one of your mesh points in your mesh, and then you can look it up in the table, right? So it's all constant time. And this is how it could look like. So you have lots of those mesh points that you calculated. This is probably something like 10 meters, 5 to 10 meters here on that map. And you have original points as before, right? And again, you have the green and red, the ones that we found or we didn't find. Okay, so let's move to some experiments here. Okay, so I wanted to test the algorithms, not the distribution and big data stuff. So this was just done on one single machine, just a laptop like this one. Now, I used, as you can see, as the data set, I used OpenStreetMap, by the way, has this great functionality that you can download the roads for any region. I'm not sure where they're in the world, probably in the world, but definitely in Poland and the whole of Europe. So I did that. There is about 250,000 roads in Malopolska region, which has the area of 15,000 square kilometers. So it's not a huge region, as you can actually see for comparison on the map. But on the other hand, when you're talking about the case of delivering goods to the customers, you would be talking about smaller regions still, right? You wouldn't be talking about the whole Malopolska. There would be a shop with like, I don't know, maybe 30 kilometers radius or something like that. So once I had those roads, I sampled some of those roads and then just tried to give a bit of randomness to where the points would be. So I just picked some points on the roads and just randomly spread them around the road with the Gaussian distribution. So essentially, more or less, you would have 95% of the points within the 2 meters of the road. But some of them would be potentially pretty far away. Then for every point thus generated, we would actually run the algorithm to look up the roads that are within 10 meters radius of that point. And obviously, as with benchmarking, there was a Warmup run, and there was some 5 iterations doing the same thing over and over again from the very start, just to see, just to warm up JVM and make sure that you don't have any random, or you level out the random noise in running it. Now, and here are the results. So here you have the count of the roads that was used. So obviously 250,000 is the number that is the whole region, but I also did it for some smaller subsets just to make sure that, just to see how it is. So each point here is one run, right? So you'd have one run that took 80 seconds in the naive case, so the basic case, and it took, actually you don't see it, but on the next one, when you have the logarithmic scale, it took 34 milliseconds, right? So this is the 1,000 times improvements that I was talking about, right? This lookup was actually 1,000 times quicker in this case. I have some more. So essentially, this shows when you change the number of points being looked up. So this is the other part of this complexity checked out. And it should be linear here, right? So for 8,000 points on 250K roads, you had 34 milliseconds, you have 16 with twice as few, and again, so it's sort of linear, right? So, just for confirmation there. And just to show up, those iterations, how they varied, and indeed the first iteration still sort of was taking a bit longer than usual. Okay, obviously there is downside as well to the approaches, and as I said, if you're trying to be clever with the algos, there are some downsides. One of them is the approximation that we mentioned, but the other one is that you actually have to store that hash table, right? That lookup table. And here is the sizes for the whole of Malopolska region, which is 250K roads. You would have, if you have the mesh size of 10 meters, so one point is 10 meters away from the other, then the size of the file would be, well, not very optimized, but zipped. It would be about 100 megabytes, right? So it's still, for the whole of Malopolska region, you could have a mesh of 10 meters points stored completely within 100 megabytes file, right? So you actually take this possibly huge processing to just single machine, and you can easily do it that way. Just a summary here. So again, we talked about number of points and how long it took. The middle solution, the n1, was actually 3.6 seconds here. Okay, so I wanted to show you some of the code just to see, because that Spark thing is cool. Before we do that, actually, let me just, maybe that's going to be a bit more visible. Okay, so I have this thing that essentially you build a Spark application as a, or actually not a Spark application, as just normal application as a jar, as a benchmark. And two main parameters that you have is whether you use index or not. So if you don't use index and you don't use mesh in this case, then what's going to happen is going to run the basic stuff. So let's just run it. And we're just gonna leave it running for a while. It's gonna take some time. This is probably, yes, this is on 50,000 rows, just so that we don't have to wait 80 seconds for the results. But in the meantime, I can show you some of the things, how we do the benchmark, and this is gonna explain a bit. So here's the benchmark for the mesh, and we have the benchmark for something I called here distance join query. So this is the benchmark for using the GeoSpark and looking up either the naive solution or the one with spatial data structures. So the main point here is, if we go to the very end of it, GeoSpark gives you this join query thing where you can just say, okay, I want to join two data sets. This is the graph of the roads. This is the graph of GPS points. Well, not the graph, the data set of GPS points. And you say whether, you want to have an index or not. Obviously some other parameters as well that we won't go into, but that's all you do, right? So once you've done that, you can, so this gives you the full set of joined. So essentially for a point, you would have all of the roads that are crossing with those points. Actually, these are not the points, but what you do also, that's another technique in GeoSpark. Out of the points, you create those circles. So you say, okay, I want to have the meters, essentially the interval that I want. So essentially, I want within, for a given point, I want to see all of the roads within 10-meter radius, right? So you create a 10-meter radius circle around that point, and then you join that with the roads. So it's pretty simple, as you can see. One thing that I wanted just to show you is, as you can see, I have this log time thing that shows you the specific sections, how long they took, so that it's easy to look up. So we are focusing on the lookup section. So by now, probably we have those things. So if we look for lookup here, on this screen it's not going to be, or maybe it doesn't have to be that small. So there is, probably I need to make it a bit smaller, but okay, it doesn't help. Anyhow, for the lookup, this solution actually took about 16 seconds, and there is a couple of iterations there, so you would see, 16, 15, 16. At the very end, there is some statistics on this. If we, however, if we go to this thing and run the mesh with indexing, right? And we go back again and we run it, it should be quicker, right? That should actually be about 1 second. Obviously, I checked that before. I didn't want to just check out with the audience here what it's going to be. But we're gonna get some results here. Here we go. So it's about 1 second with this sort of indexing approach. But just coming back, just to show you the mesh approach, all you do here initially, you create the mesh if it hasn't been created. Initially, there is a special logic. We probably won't have time to go through that, but we can discuss that later, how I actually create the mesh. And then the lookup is just, you have this mesh, and this is just a lookup table. You get a coordinate on that mesh. And here is a lookup as well. So coming back to our little test, so it was indeed about a second that it took each time. Now, if we change that to our run, and we say, yes, we do actually want to use mesh, and you do the same test, you're going to have the final result there. Okay, so let it just run. And in the meantime, do we have... Okay, so this is the old one. Okay, excellent. So some nice questions here. Just to... sorry. Okay, we're going to see them here. Okay, and as you can see, well, surprisingly or not, The lookup actually took, the 30 milliseconds as we expected, but it is a bit long, right? And the total run actually took 17 seconds. And, you have it explained by here. So we don't generate mesh here, but we actually load it up. And it's big enough. Again, it is not very optimized. It actually takes 16 seconds to load the mesh up, first of all, so that you can look it up quickly later on. I guess not surprising. Obviously, it's still, for what we want to do, let's imagine you would like to have the service that responds very quickly to the lookups. It's not a problem because you just load it up once at the very beginning and that's it, right? And then you can enjoy your millisecond lookup time later on. So I guess that's it. We've reached the time by now. I know I'm conscious we have lunchtime now, so I don't want to stop you for too long, but there is one question here. So how long did the generator of the mesh data take? The generator took, in this particular case, about an hour to generate that mesh. It used, 8 cores. I actually have that at the rest of the presentation, but we're just not going to have time. But maybe there is. So there is a whole. Oh, here we go. So there is 100 million points on a 10-meter distance mesh, because you have this 15,000 square kilometers. So if you multiply that by the amount of points, you get 150 million points, and it took about 120 megabyte file to actually store this. Size and how dense was the mesh. So I guess I answered all of those questions here. Are there any other questions, or are we ready to go for lunch? You're talking about the specific real-world case. It was the basic solution to make it simple. Because again, it didn't matter too much in the grand scheme of things of this business case. But some of the business cases might use that a lot. Okay, so thank you very much. There is going to be lunch now served at where the stands are. So please enjoy and do grab me later on. And we meet back here in 1 hour at 2 p.m. All right, thank you. Thanks.